Okay, so my goal in this video is to show us how to find the arc length S. So usually we use S for arc length of a smooth curve, so differentiable in this case. So a smooth curve F from A to B. Okay, so what do we mean by that? Well, if we have a nice function here, call it f, and we have a closed interval a to b, basically what we're saying is if I were to lie a tape measure along this curve from this point A f of A to this point B f of B, how long would that curve be? So much like we did when we were computing area, what we're going to do is we're just going to break this thing up into a bunch of rectangles again, right? But here, what we're going to do is we're basically going to zoom in to these little triangles that get formed here, because very roughly I can treat that little piece of the function as a hypotenuse of one of these right triangles. And so in order to compute our arc length, basically all we're going to do is add up all of those hypotenuses. So if I have just some point x over here, so let's say that's x, and remember we're going some distance away, delta x, and so this is x plus delta x here. Okay, so that means that the base of each of these triangles is delta x, and to get our height, well, our height at x is y, or f of x, and our height here is f of x plus delta x, right? Which is exactly equal to y plus delta x in this case. So that's our change in y. Okay. Oh, excuse me, not delta x, delta y. Okay, so then we can use our Pythagorean theorem to get our hypotenuse length. So the hypotenuse there has length square root of delta x squared plus delta y squared, right? And now what we're going to do is a little trick. So what I'm going to do is I'm going to factor out delta x squared, and I'll come back up into that space to the right in a minute. But if I factor a delta x squared out here, I'm left with 1 plus delta y squared over delta x squared. And since we're only dealing with positive values, I can pull the square root of delta x squared out of my radical without having to worry about an absolute value sign. And this is the same thing as 1 plus delta y over delta x squared. Okay, so we have this expression. Now I want us to recall our mean value theorem. So our mean value theorem tells us that so if we have all these conditions satisfied, right, our function is continuous on the closed interval, differentiable on the open interval. If that's true, there exists some value c delta x such that our derivative is equal to the difference quotient, basically, right? And this f of x plus delta x minus f of x is exactly our change in y, right? So our mean value theorem tells us that there's some place where our instantaneous rate of change, or our derivative, is exactly equal to the actual change in y over the actual change in x. And since we're requiring up here that we have a smooth function, the mean value theorem applies. So what I'm going to do is I'm going to replace delta y over delta x with the derivative, and I'm going to add all of these things up from a to b using an integral. So we get that our arc length is going to be the definite integral from a to b of the square root of 1 plus f prime of x squared dx. And I'll just do one quick example to show us how this works. Let's see, what's a good yeah, so let's say I have the function y, so this is an example. So let's say I have the function y equals 3/2 x to the 2/3 plus 4, and I want to compute the arc length on the closed interval 1 to 27. Okay, so first thing we need to do is find our derivative. So in this case, that's just y prime. Conveniently, the 3/2, the 2/3 cancel. Derivative of the constant is 0, so we're just looking at x to the negative 1/3, or 1 over the cube root of x. So my arc length s then will be the definite integral from 1 to 27 of the square root of 1 plus 1 over the cube root of x squared dx. And that same trick that we used to derive this formula where we factored out that delta x squared, that's going to be kind of a handy trick to use when you're trying to compute these arc length integrals. So what I'm going to do is I'm going to factor out 1 over the cube root of x squared. So we're looking at the integral from 1 to 27. Eventually I'll just go ahead and pull this thing out of the radical, but for now I'll leave it in there. So 1 over cube root of x squared. And when we do that, under the radical, we're left with the cube root of x squared plus 1. Okay, so, well, why did we do that? So first, I'm going to bring that outside of my radical. And I'm looking at 1 over the cube root of x times the square root of the cube root of x squared plus 1 dx. And now we can do a bit of u substitution. So let me, oops, oh, purple. All right, so I'm going to do a bit of u substitution, and it's nothing weird, kind of what we would expect. We're going to let u be that stuff under the radical, which I'm going to write as x to the 2/3 plus 1. And hey, what do you know? Conveniently, we get a constant multiple of x to the negative 1/3. And we have 1 over cube root of x dx, so I'm just going to write this as 2/3, not 2/3, 3/2, excuse me. So 3/2 du is equal to 1 over the cube root of x dx. All right, now at this point, rather than changing my limits of integration, I'm just going to do an indefinite integral for now. So I'm just going to compute the indefinite integral of 3/2 u to the 1/2 du, because that's essentially what we have after we substitute back in. And so then remember our power rule for integrals. I'm going to add 1 to the 1/2. That's going to give me 3/2. And then when I divide by 3/2, I'm just exactly going to get u to the 3/2. So that's kind of cool. So this is, yeah, so this is u to the 3, I don't know what I'm writing, u to the 3/2. And in this case, it would be plus a constant, but we're gonna substitute back in at this point. Okay, so from here, boop, what we have is the square, no, what do we have? That stuff to the 3/2. Yeah, so I'm going to write this as the square root of x to the 2/3 plus 1 cubed. And we want to evaluate this from 1 to 27. So that's, you know, quite a bit going on there, I guess. But when I plug this in, let's see, what do I have here? I have the square root of 27 to the 2/3 plus 1 cubed minus the square root of 1 to the 2/3 plus 1 cubed. And so let's see, what does this give us? Cube root of 27 is 3, 3 squared is 9, 9 plus 1 is 10, so square root of 10 cubed is 10 square root of 10, 1 to the 2/3 is 1, plus 1 is 2. Square root of 2 cubed is 2 square root of 2, and I'm going to leave my answer just like that. And that's basically how you do these.